All right, I'd like to do 3 problems with you from the 3 sheets that I gave you in class. This is the second page of the Absolute Extrema worksheet. So I'd like to do problem 12 with you. And the reason I'm picking this problem, first of all, it looks nasty, but second of all, I'm picking it because several of the problems on this second page do not have the closed interval that the Absolute Extrema problems that we've looked at before required. All right, so I just want you to see what to do in these cases. So we'll take a look at this one, and then when you hit some of the other ones, you'll know what to do. And again, I'm so sorry that there's not that much space on these problems for you to do your work. So if you feel like you need to move to another sheet, please feel free to. I might need to do the same thing partway through. All right, so again, for absolute extrema, we're checking to make sure that the function is continuous on a closed interval. So we're going to look at this as, we're going to look for continuity. Clearly we don't have the closed interval. What that means is that there is no guarantee that there will be an absolute max or an absolute min on that interval. Because again, we saw before in some problems that if you had something like this, here was your A and here was your B, and the endpoints weren't included, it's possible that you would have no max or min on that interval because the endpoints aren't included. So I just want you to see what to do in cases like this where it's not included. Again, some of them will have a partially closed interval, like these. Some of them will have a completely open interval. Sometimes they'll have a completely closed interval. So I just want you to see what to do. All right, so if you remember, the first thing that we have to do is find the critical values. And in terms of finding the critical values, we have to take the derivative. So we've got y prime equals, all right, the derivative of this would be, bring that down, so we've got negative 1/6 times the 7/3 that we bring down, x plus 1, decrease the power by 1, so this is going to now be to the 4/3. And again, we have to take the derivative of the inside for the chain rule, but it's just 1, so I'm going to skip that part. I don't want you to think I'm not thinking about it, but we just don't have to write it. All right, plus, and then the derivative of this, we're going to bring that down. I'm just going to write that as at once as 14/9 times x plus 1 to the negative 2/3. All right, and again, the derivative of the inner function right there is just 1, so we don't have to write it. Right, I'm going to get rid of this negative 2/3 fraction, and I'm going to get rid of these denominators. Actually, let me just real quick write this as negative 7/18. So when I go through and multiply, I'm going to multiply to get rid of the fractions, and I'm going to get rid of the negative exponent. So when I do that, I need to multiply by 18 to clear the denominators, and then I need to multiply by x plus 1 to the 2/3, and do the same in the bottom, x plus 1 to the 2/3. All right, when we do that, we end up with y prime equals negative 7, all right, x plus 1 to the 4/3 times x plus 1 to the 2/3. That gives us x plus 1 to the 6/3, which is x plus 1 squared. All right, now let's do the same thing here. When we multiply this by 18, the 9 here cancels with the 9 in here, leaving a 2, so this becomes plus 28. And then this part is just canceled out by the x plus 1 to the 2/3. In the denominator, we get 18 x plus 1 to the 2/3. All right. I'm going to multiply the top out. Again, we're looking for where the denominator, where the derivative is 0. That's going to come from where the numerator is 0, and where the derivative is undefined. That's going to come from when the denominator is 0. So let's just multiply this out. X plus 1 squared is x squared plus 2x plus 1. So when I distribute that negative 7 through, I've got negative 7x squared minus 14x plus 1 plus 28. And the denominator here is going to stay 18x plus 1 to the 2/3. All right, if I combine these right here, I end up with y prime equals negative 7x squared minus 14x plus 29. All right, actually, you know what? I'm just looking at my notes. It's probably easier if I solve this using, all right, sorry. All right, let's take and look. We want to do two things. When is this 0? Negative 7x plus 1 squared plus 28. When is that 0? That's going to tell us when our f prime is 0. Here's what I should have done. It's just a little bit easier. If I take and move the 28 over to the other side and divide by negative 7, I get x plus 1 squared equals 4. Again, this becomes negative 28 when I move it over, but then I divide by negative 7 and I get positive 4. I'm going to take the square root of both sides. Again, it's been a while since we've done something like this. I know we have a long time ago, but it's because this is a pure quadratic, because all of the things are lumped together in a squared form. So when we do that, we can just not multiply that out, move everything over and solve that way. All right, so if I take the square root of both sides, I end up with x plus 1 equals plus or minus 2. And then if I add 1 to positive 2, I get x equals 3. If I subtract 1, that's not right. If I subtract 1 from positive 2, I get positive 1. If I subtract 1 from negative 2, I get negative 3. All right, so this is where the derivative is 0. So those are part of our critical numbers. And then we want to see when is the denominator equal to 0. Because that is when the derivative is undefined. All right, and so we are going to say that 18 times x plus 1 to the 2/3 equals 0. Hopefully you can say that's when x is negative 1. All right, what that means is the function is not differentiable at that point. So it's either going to have a sharp turn there, or it's going to have a vertical tangent line. All right, but either way, we need to then put them into the table. All right, so these are our critical values. So we've got x, f of x. All right, our x values are negative 1, negative 3, positive 1. I'm also going to put the endpoints in there. I know we're not supposed to, but I just want to see if they were included, would they be the max or the min? Because if I get something that's high right here, but one of these is higher, then I know that's not actually the max. If I get something here that's low, but this is even lower, then I know it's not the min. So I am going to put those in. And then we're going to plug them back into the original function. I'm sorry, this is so horrible. I'm just going to tell you some values, and you can verify them. So if I put negative 1 in, I end up with, I guess I just got zeros everywhere, because negative 1 plus 1 is 0. That means this is 0. That means this is 0. Same thing on the other one. So this, sorry, I shouldn't be pointing to this because that's the derivative. I should be pointing right here. So negative 1 is 0. When I plug in negative 3, I get negative, sorry, this also should be negative 5. I plug in negative 3, I get negative 5.04. I plug in 1, and I get, where did I get the 1 from? Oh, I know why. We don't count the 1. Sorry, I'm going to cross that out because it's not actually in our interval right here. All right, so while it was a critical value of this, we get to cross it out. Sorry, I forgot to do that. If I plug in 0, I end up getting 4.5. And again, you should check these on your own. I'm just doing this because it saves a lot of time. And if I put in negative 5, I get negative 3.17. Right? So I'm looking at this list to see where the maximum value is and where the minimum value is. So if you look at all these y values, you see that this right here is the maximum. Sadly, it's not included, all right? So we can say no max. All right, then I look to see if I can find the minimum value, right? It is right here. That is a valid point right there, okay? Again, if it had shown up as -5, we would say, sorry, that's not it. So this is one of the critical values of the function. It's within that interval, and it's not one of the endpoints. So the min is at the point -3, -5.04. All right, so again, I still included those 2 points in my test values because I wanted to see if the max occurred at that point, then we would know not to include it, which is exactly what happened. And same thing with the min. Had this been like, let's say, -6.17, then we would have said there's also no min in that interval because it's lower than the min at a critical value. All right, so, but that's not what happened. It occurred at a point that was within the interval. And so this is the min of the function. All right. The other ones are much, much neater than this. And so hopefully that won't be a problem. But I wanted you to see what to do for those specific ones where it's open at an endpoint. Okay. I'm going to pause for a minute and come back with the Rawl's theorem and the mean value theorem. Okay, let's take a look at one Rawl's theorem problem. This is on the Rawl's theorem worksheet, so, but it's on the second page, and it says right here, for each problem, determine if Rawl's theorem can be applied. And if it can, find all values of C that satisfy the theorem. If it can't, explain why not. So the first thing we have to do is make sure it can be applied. So if you remember from our notes on section 3.2 for Rawl's theorem, there are 3 things that we need to check. First is that f is continuous on the closed interval. The second is that f is differentiable on the open interval. And that third, f of A has to equal f of B. All right, again, continuous just means you're not going to have any denominators that are 0. You're not going to get any negatives under a radical sign, for example. For differentiable, we're looking for no sharp turns or places where it's undefined. In other words, where the tangent line would be vertical. So in a situation like this, let's say if that were the derivative, if that were the function, the derivative there would be undefined. And then this is obvious that the value at the endpoints has to be equal. So let's check this. I'll do one, talk you through it, and then that should hopefully give you enough information to do the other 5 when I assign them. All right, so we're looking to see, first of all, is this continuous on the closed interval -3 to 4? All right, so first of all, let's look to see if there's anywhere that it's discontinuous, and then we'll see whether that falls in our interval. So in order for it to be discontinuous, since this is a rational expression or rational function, we're looking to see where the denominator would be 0. Right, and that would occur at x equals -4. So I'm going to say discontinuous at x equals -4, but I look to see if that's in my interval, and it's not. It falls just to the left of the left endpoint. So even though this does have a discontinuity, we can't see that when we're just focusing on this interval here. So is f continuous on that closed interval? Yes, it is. Right, then we want to know if f is differentiable on the open interval. And again, without finding the derivative, you just kind of have to think of what is the derivative going to look like. So for this particular one, we would use the quotient rule. So in the numerator, we would have bottom times the derivative of the top minus the top times the derivative of the bottom. So essentially, f prime is going to be some sort of polynomial numerator all over the bottom squared. So x plus 4 squared will be the denominator. So again, some polynomial numerator, which is fine, but then this x plus 4 squared in the denominator will have a 0 at -4, making the derivative undefined there. In other words, the f would not be differentiable at that point. So again, it's that same point that we found here, but since it's not in the open interval, -3 to 4, it's fine. All right, so we just want to make sure that there are no discontinuities in here and no spots where it's not differentiable in the open version of that. We just did that. Third, we need to check to see that f of a equals f of b. So in other words, is f of negative 3 equal to the same thing that f of 4 is equal to? All right, so let's check that. Negative 3 squared is 9. Minus a negative 3, that's going to be plus 3, minus 12, all over negative 3 plus 4. So in the numerator, we end up with 0 over 1, or 0. In the denominator, we're going to put, in the second value here, we're going to put in 4, and we get 16 minus 4 minus 12 over 4 plus 4. In other words, we get 0 over 8, or 0. So is f of a equal to f of b? In this case, yes, it is. That says that we can apply Rawl's theorem. Rawl's theorem, if you remember, says that if the function meets these conditions, then there is somewhere in this interval where the instantaneous rate of change, in other words, the slope, is also 0, the average rate of change. All right? So that means that we need to take the derivative in order to find that point or those points that they're talking about. Right? At this point, I might recommend to you to switch to a new piece of paper if you have not done so already, because there's just not a whole lot of room here. When I write the answer keys, I don't show all my steps, so I will not be able to fit everything in here as I'm talking through. So I'm going to extend into another cell here. So I need to find the derivative. All right, it's bottom times the derivative of the top, so x plus 4 over 2x minus, times 2x minus 1 minus the top, x squared minus x minus 12, times the derivative of the bottom, which is just 1, all over the bottom squared, x plus 4 squared. And we are going to distribute this. So x times 2x is 2x squared. X times negative 1 is negative x. And then 4 times 2x is 8x. So 8x and negative x is negative 7x. No, sorry, positive 7x. And then 4 times negative 1 is negative 4. Minus x squared plus x plus 12 all over x plus 4 squared. All right, I'm going to clean up the numerator. X squared minus x, 2x squared minus x squared is x squared. 7x plus x is plus 8x. Negative 4 plus 12 is positive 8, all over x plus 4 squared. So it guarantees that there is some place where this function, the derivative, is equal to 0, right? And I have to figure out what that is. Now again, when we've got a fraction like this, the only place that this can be 0 is when this equals 0. So really what we're going to do is say, I want to know when x squared plus 8x plus 8 equals 0. Unfortunately, that's not factorable because this is, I'm looking for two things that multiply to 8 that also add to 8. That's not possible. So we could either do completing the square or we could use quadratic formula. So I think I did quadratic formula probably. So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And so I end up with 8 plus or minus the square root of 64 minus 32, which is 32 over 2. This contains a 16, so I can pull that out as a 4. So it's 8 plus or minus 4 root 2 over 2. I can simplify all the outies. So this becomes 4 plus or minus 2 root 2. Right? The negative version is not in the interval. That's saying 4 minus 2 root 2. Let me just, I'm sorry, it's actually
Sorry, I dropped a negative, I dropped a negative, I dropped a negative. Yeah, so that is not in the interval right there. -4 minus 2 root 2 is way too small, because 2 root 2 is going to bring you somewhere around -3 something. So -4 minus roughly -3 is going to be -7-ish. But -4 plus 2 root 2 would be in that interval. So that -4 plus 2 root 2 is the value of x that we're searching for right there. All right, again, the negative version is not in that interval. All right, so that would be the solution that you would do for this. All right, so again, we checked to make sure it was continuous on the closed interval, differentiable on the open interval, that the endpoints were equal. And so then once we confirmed all that, then we took the derivative. And then because this was a rational expression or rational function, we set the numerator equal to 0 and then solved and eliminated any values that they gave us in here that were outside our interval. So outside that -3 to 4. All right. So not all of them will work, but I think most of them do work. All right. And when I say work, again, it says, can Rawl's theorem be applied? I think there's like maybe 1 or 2 cases where it doesn't apply, but the rest of them should. Okay, let's take a look at the second page of the mean value theorem worksheet. All right, this again is one that I handed out to you in class. We're going to take a look at problem number 13. Again, I picked this one because we don't have a ton of experience with fractional exponents in terms of not necessarily taking derivative, but just what do they mean. So I figured this would be a good example. Okay, so again, for the mean value theorem, we have only 2 hypotheses that we have to satisfy before we can apply the mean value theorem. So the first is that f is continuous on the closed interval, and the second that f is differentiable on the open interval. Again, so this is similar to what we had for Rawl's theorem. The thing that's missing is that f of a has to equal f of b. So we just have to check these 2. The conclusion then, if we can show that these 2 are true, is that the average rate of change over the interval, in other words, f of b minus f of a over b minus a, at some value c has to equal the instantaneous rate of change at that point, right? So the average rate of change over the entire interval equals the instantaneous rate of change at some point. All right, so let's go through each of those things for problem 13. All right, so first we're going to check for continuity. Really a big part of this plays off of the exponent. This is telling us to take the cube root of whatever's in here and then square it. So cube root, there are no restrictions to the domain in that we can take cube roots of positive numbers or negative numbers alike. So we're not going to run into any problems with that. And then we can square any number we want. All right. So regardless of what ends up in here, we can raise it to the 2/3 power without any trouble. So it's continuous everywhere, specifically on our interval. So continuous, yes. All right, then we have to see if it's differentiable. And again, we don't have a ton of experience with differentiable when it comes to fractional exponents, but I have warned you a number of times that, again, the V shape for non-differentiability comes from absolute value, and then it being undefined for other reasons often comes from a fractional exponent, and that would be the case here, because what we're looking for is some sort of function where there is the point where the tangent line is vertical, right? And that often happens when we have a fractional exponent between 0 and 1. So here's what we need to think about. When I take the derivative of this, I'm going to have to use the chain rule. I'm going to bring the 2/3 down to the front, so I'm going to get a negative 2/3. I'm going to leave this inside part alone. I'm going to decrease the power by 1 to give me a negative 1/3, and then I'm going to have the derivative of the inside here. What's going to happen is this is going to flip to the bottom and become an 6 plus x 6x plus 24 to the 1/3 in the denominator. So when we get the derivative, it's going to look something like this. We'll have some function up top, and then we're going to have a 6x plus 24 to the 1/3 in the denominator. So we will end up potentially with some place where this is 0, and hence the function is not differentiable. So we have to figure out when that will be. Hopefully you can tell just by looking at this, it's going to be x equals -4. So x is not different, or f of x is not differentiable at x equals -4. We think, dang, that's in our interval. However, remember, it has to be differentiable on the open interval. So the open interval does not actually contain -4, right? So, but that's okay, because -4 is not a member of the open interval -4 to -1. Right? Had it been something like -5 to -1, we would be out of luck there, because -4 would be in that interval. But since it ends at -4 and doesn't include -4, we're okay. So yes, it's continuous. Yes, it's differentiable on the open interval. So now we can apply the mean value theorem. And again, the mean value theorem says that we have to find f of b, which is, I'm going to go with -4, minus f of a. I'm going to go with -1 over -4 minus a -1. Again, you could reverse the order of all these and that would be fine. So f of -4, if I plug that in, I get 0 in here. Doesn't matter what power I raise it to, or if I change it negative, it's still 0. Minus, right, now be careful here, because there's a negative out front, and then inside we're going to get -1 times 6 is -6, plus 24 is 18 to the 2/3 power, all over -3. And when I do that, this 0 minus a negative is going to change this to plus a positive, and then the 0 won't do anything. So this is going to end up as 18 to the 2/3 over -3. Now, I realize that 18 is not a perfect cube, but I think it's going to be to our benefit in terms of accuracy, not getting a rounded answer, but getting the exact answer if we actually try to figure out what this is or simplify it. So without a calculator, I would say that 18 is the same thing as 3 times 3 times 2. I just did its prime factorization. So 18 squared, again, that's what it's asking us to do. Square it and then take the cube root, or cube root and then take the square of it, but I'm just going to square it first. And I'm not going to actually write anything out in terms of the value. I'm just going to write out all its factors. So 3 squared squared is 3 to the 4th, and 2 squared is 2 2s. All right, now if I were to take the cube root of everything, right, the cube root of this, things can come out if they are in sets of 3. So here I have 3 sets of 3, which means this is going to come out as a 3. And then I'm left with a 12 inside. So it's 3 times the cube root of 12, all over -3. These 3's will cancel, and this is going to leave us negative the cube root of 12. Again, we'll just get a more accurate answer if we use that instead of doing a decimal approximation. All right, so that was this side of the equation. All right, now it's telling us that there is a c value in here, so that when we take the derivative and set it equal to negative cube root of 12, that we'll find that c value. I'm going to do it down here, just to give myself a little bit more space. Again, I encourage you to work on a different sheet of paper with these because they're so cramped. All right, so now we need to find the derivative of f. All right, so when we do that, we're going to bring the exponent down times the negative in front. So we're going to get negative 2/3, 6x plus 24, all to the negative 1/3, times the derivative of the inside. Again, this is the chain rule right here. I'm going to combine these two to get the 3 in here will cancel, so we get negative 4, 6x plus 24 to the negative 1/3, or if I rewrite that, I'm going to get negative 4 over 6x plus 24 to the 1/3. And I want that to equal the negative cube root of 12. So I'm going to have negative 4 over 6x plus 24 to the 1/3 equals negative cube root of 12. I'm just going to cancel out these negatives. In other words, multiply both sides by negative 1. So this will go away and this will go away. And then I see that both sides involve a cube root. So I'm going to cube both sides. When I do that, in the numerator I get a 64, and in the denominator 6x plus 24. And over here on the right, the cube root of 12 cubed is 12. All right, there's simplifying that we could do here, but let's just do it all at once, or as it becomes really necessary to do it. I'm just going to cross multiply. So this is going to give me 64 equals 12 times 6x plus 24. I'm going to factor out a 6 here. I know this is unconventional, but 6 times 12 is 72, and then this is x plus 4. The reason I'm going to do that is because now both of these contain an 8, which I can cancel out. So this becomes 8, and this becomes 9. We end up with 8 equals 9 times x plus 4. How about I just write that as 9x plus 36. I'm going to subtract 36 from both sides, so I end up with negative 28 equals 9x. Divide both sides by 9, and I get x equals negative 28 ninths. And that is the C value that mean value theorem guarantees. So that at the point negative 28 ninths, actually let's just confirm that that is actually in the interval. It really should be, but 9 goes into that 3 times. This is negative 3 1/8. So yes, that is in the interval. But it says that at negative 28 ninths, that the slope of the tangent line at that point is equal to the slope of the line, the secant line that goes through the two endpoints. Okay, that's it. Bye.